First of all, I want to thank Professor Vahid Khoury for inviting me to participate in this conference. I wish I could be in Iran with the rest of the participants of the conference, but unfortunately, the best I can do is the Zoom presentation from St. Louis in the United States. I'm going to begin by giving a preface of what I intend to talk about in this presentation. First of all, I'm going to start with something that everyone here knows very well, namely that in a solid tissue, cells are embedded in a viscoelastic extracellular matrix, which is composed mainly of fibrous collagen and other proteins and proteoglycans and other components as well. The biochemical and biomechanical properties of the matrix have a very big effect on determining the differentiating form and function of the cells embedded within it. I'm going to say a little about that later. Therefore, in order to preserve the form and function of the cells, like muscle cells or nerve cells or whatever, in the matrix, the biomechanical properties have to be maintained at a steady state. And that's this homeostatic biomechanical steady state that I'm talking about here. And it's the purpose of the fibroblasts in the tissue to maintain this steady state. So under normal conditions, fibroblasts exert small forces and secrete materials like collagen, for example, to maintain the steady state. But under some conditions where there's a serious distortion of the condition of the tissue, so wounding, for example, then the fibroblasts in the vicinity of the wound transform to myofibroblasts, which are cells with a phenotype somewhere in between smooth muscle cells and fibroblasts. And so they have they're both more contractile than normal fibroblasts, and they have synthetic capabilities for making collagen and other matrix material, which suits them well to repair serious damaging to the tissue. So I am going to spend most of this time talking about a model for the transformation of fibroblasts to myofibroblasts. And an important point to begin with is that cells in tissues adapt to the mechanical properties of the extracellular matrix in which they're embedded. And this was very nicely shown by Engler and others in the reference that's cited here, and as there have been since other verifications of this fact, namely what Engler and the others showed was that soft matrices that mimic brain tissue, actually stem cells that are embedded in these soft matrices develop into nerve-like cells, whereas stem cells that are embedded into stiffer matrices that are more like muscle tissue become more like muscle cells. And finally, cells that are embedded in rigid matrices that mimic collagenous bone become more like bone cells. So that shows you then that the biomechanical properties of the extracellular matrix have an important determining effect on what stem cells embedded in the matrix become, whether nerve, bone, or muscle, or any other kinds of cells. So that means that it's important that fibroblasts and myofibroblasts are able to maintain the matrix in an appropriate biomechanical state. In particular, normal fibroblasts under normal conditions maintain the normal homeostatic biomechanical steady state that we have under most circumstances. On the other hand, if there's wounding, then the normal fibroblasts undergo transformation to myofibroblasts. And as I pointed out before, the myofibroblasts are well suited for repairing more serious damage to the tissue by their increased synthetic capability and their ability to exert contractile force on the matrix and thereby close the wound. And this is very nicely discussed in a by now somewhat old review by Hintz, which describes especially the biomechanical characteristics of the transformation of fibroblasts to myofibroblasts. In particular, the observation that the stiffening of the matrix enhances the probability that fibroblasts become myofibroblasts. But let's begin now with the recognition that myofibroblasts, which exert contractile forces on the matrix filaments, can stiffen the matrix in a local area by exerting these contractile forces. And you might expect that that stiffening effect would be a relatively short-range effect. Nevertheless, it's been observed in papers, some of which are cited here, that when a myofibroblast exerts contractile force on the viscoelastic extracellular matrix, the stiffening effect actually occurs over a fairly large, although still limited range, maybe a range of the order of 100 or more microns. Now, the next thing that I want to mention to you is a justification for my statement earlier that the stiffening of the extracellular matrix increases the probability that a fibroblast will become a myofibroblast. And these two references demonstrate that. And there are many others since then too. The magnitude of the stiffening, I am asserting that the magnitude of the stiffening increases with the number of myofibroblasts that exert contractile force on the extracellular domain. In other words, I'm asserting what you would expect, namely that if you have more myofibroblasts exerting contractile force on a local domain of the extracellular matrix, that extracellular matrix will stiffen to a greater extent than just one or a few myofibroblasts exerting contractile force on that domain. And that can lead to a positive feedback because, as I said, when stiffening is increased, there's an increase in the probability of fibroblasts becoming myofibroblasts. And so the more fibroblasts become myofibroblasts, the higher the stiffness, and therefore the higher the growth rate of the number of fibroblasts in the matrix. And so that's a positive feedback. The more myofibroblasts you have, the more myofibroblasts you will generate. Now, this then will also lead to the notion that what's going on in formation of these clusters of myofibroblasts, let me just emphasize now that if you have a few myofibroblasts generating more myofibroblasts to join that cluster, then that's how clusters grow, and that's why I'm calling this a cluster model. So the cluster increases more rapidly the higher the number of accumulated myofibroblasts, and that, as I pointed out before, was a positive feedback system. Now, this is a somewhat technical issue that I just wanted to mention, which is that the transformation of the first fibroblast in this domain to a myofibroblast occurs without any increased stiffness from previous myofibroblasts. And so therefore, I'm supposing that the formation of the first myofibroblast from a fibroblast is much less probable and therefore occurs much more slowly. And therefore, I'm calling that a kind of nucleation process. The nucleation of a cluster is slow compared to the growth of the cluster. So that is the basic idea behind the cluster model. But in addition, I want to mention that this is not only a biomechanical phenomenon that has to do with tissue stiffness, but also cytokines are very important. And in particular, TGF-beta is the major cytokine that influences that accelerates the transformation of fibroblasts to myofibroblasts. I'm not going to talk about this more, but it's important to keep in mind for the future. So this is the basic idea behind what I'm talking about. So suppose you have a number of clusters, might be one or two or several, clusters that have J myofibroblasts in them. Now, in the vicinity of one of those clusters is are fibroblasts, which are not activated, they're not myofibroblasts. And the influence of the cluster on a nearby fibroblast will accelerate its probability of becoming a myofibroblast, which then joins the J cluster and makes it into a J+1 cluster. So that's like a chemical reaction, a second order chemical reaction of fibroblast and a cluster encounter one another to form a cluster with one additional cell. Now, it's not because the fibroblasts are diffusing around. This is solely based on proximity of the fibroblasts to clusters of myofibroblasts. So just for technically looking at the model, as I pointed out, N of J is the number of clusters with myofibroblasts. Kf of J is the forward rate constant for the growth of a J cluster to a J+1 cluster, and Kb of J is the rate constant for the reversal of that. Now, the completeness of the model requires that we define a Kb of J, but I'm not going to say much about that in the future. Just for simplicity, I'm going to suppose that Kb of J is a constant independent of J. So these are the individual reactions. A J-1 cluster becomes a J cluster. That's what I call a propagation reaction for the growth of the cluster. But the first reaction is the transformation of a fibroblast to a myofibroblast in the absence of any clusters. And that's the nucleation reaction. And the rate constant for that, sigma F, and the reverse renucleation constant, sigma B, is much smaller. The sigma values are much smaller than the Kf and Kb values because the nucleation reaction is much slower and much less probable. So this is the overall cluster mechanism, a series of second order reactions, or if you're like second order chemical reactions. I don't want to spend a lot of time on this. This is the way that the model was implemented in a mathematical form. And these are the kinetic rate equations. Again, I don't want to spend a lot of time on this. One can solve these using MATLAB or some other mathematical software, which is what I did. And the important point here is that the form of the rate constants and the values of the parameters like Kf, Kb, S, and so on, they have a big effect on the nature of the transformation. And in particular, I'm going to compare examples of cooperative and non-cooperative mechanisms which yield different distributions of cluster sizes. Now, a cooperative process is one in which the cells in a local region strongly influence how other cells transform into myofibroblasts. And if this influence is very strong, then you could even go to an extreme case where all the fibroblasts will transform as a block into myofibroblasts. Now that's contrasted with a non-cooperative mechanism in which the cells don't influence each other very strongly or at all in their conversion to myofibroblasts, and so therefore the cells transform independently. And now one has to decide what the rate constants actually look like. So for a non-cooperative case where there's no effect of the conversion of one cell to another cell, I'm just going to say that Kf of J and Kb of J are independent of J. They're just constants. On the other hand, you can also form the rate constants in ways in which the rate constants depend strongly on J. And here's an example of one of those. So here we have the cluster size J times a parameter S, which is the strength of the contractile interaction of the myofibroblasts in the cluster with the extracellular matrix, and then a kind of general rate constant, K sub FF, which is right here. XT is just the total number of fibroblasts. And what you see is that for this representation of the forward rate constant, Kf of J grows rapidly with J as long as Js over XT is greater than 1. So this then leads to a system in which the higher clusters have a much more probable effect on converting fibroblasts to myofibroblasts than the smaller clusters do. And this then leads to a highly cooperative mechanism. Now, a slightly less cooperative one is not to have J as the exponent, but a constant Q. So this here also for Js over Xt being greater than 1, and Q not being so big, might be 1 or 2, then Kf of J increases, but not so rapidly as the second example does. Of course, if Q were very large, then the increase in the rate constant would be all the faster. So there's a general principle here which is that Kf of J the more rapidly Kf of J grows with J, the stronger the acceleration of the transformation for larger clusters, and the more cooperative the transformation. So now I'm going to show some examples of that. Here's an instance in which Q, I'm looking at the rate constant, I'm looking at this rate constant here, where Q is a constant. And in this case, Q is given the value 1. And so Kf of J increases with J, but not so rapidly as it might if Q were larger. And what that shows is that the clusters in the numbers of cells in the various clusters, in this particular case, there are 15 myofibroblast clusters and 1 cluster of normal non-activated fibroblasts. They don't change very much. The number of cells in one cluster is rather similar to the number of cells in any other cluster, and so this is a non-cooperative process. And that's contrasted now with a situation in which I've increased Q to 2 so that the rate constants grow more rapidly with the number of cells J in the cluster, and that then leads to this all or none behavior where there's a greater tendency now for normal fibroblasts to flip as groups into myofibroblasts. And so what you see is then, for this particular selection of the parameters, is that you'll have some normal fibroblasts over here that have not flipped. This is the normal fibroblast. This is where clusters of only 1 myofibroblast, and then very few of the intermediate clusters, and then finally much larger clusters that have the largest numbers of myofibroblasts. So that's the distribution of cells for an all or none case, in which the rate constants grow rapidly with J. And you see the same thing in the kinetics of the transformation from fibroblast to myofibroblast. I don't want to spend time on this, but basically what occurs in the kinetics curves is what you see also in the final distributions. Those clusters that have the largest amounts of cells in the all or none case are the ones that appear in the most highly represented in the kinetics, and then down here are the very small clusters, and they're hardly present at all in the kinetics, just as they're hardly present at all in the final equilibrium distribution. So I want to summarize then by pointing out that the measured course of the fibroblast to myofibroblast transformation provides information about its mechanism. So if, first of all, are there clusters? If there are clusters, how do the clusters grow with the progress of the transformation of fibroblast to myofibroblast? How does the cluster size vary? Can you represent it in terms of a rate constant that has a constant exponent or a more rapidly increasing exponent, and try to get values for the general rate constant case of FF and the strength of the interaction S. And then there are also biomechanical questions, which one can answer by doing experiments and comparing with the results of the numerical model. And one thing that we certainly have to find out in the next stage of this investigation is how does the magnitude and spatial range of matrix stiffening depend on the number and distribution of the myofibroblasts in the cluster. This is something that can be answered experimentally, and we need, or somebody needs, to look at that. And there are other questions that we can ask and answer by experimental testing. I don't want to take time to talk about them, but I do want to emphasize that experimental evidence will provide the main test of the cluster model. This is something that we can test experimentally. Do we see clusters? Are the patterns of cluster development what you might expect from what the numerical model predicts? And those kinds of questions need to be investigated. And that's my presentation of the cluster model. I hope that we and other people can look more carefully at this and find out whether it's actually something that describes how fibroblasts convert to myofibroblasts. And that's all I'm going to say for now.